Good morning, ladies and gentlemen. September 30th, we are very happy and proud to share with all of you the results of LAMpAS project. This EU initiative that developed processes and a machine for structuring large surfaces. Today we will have a presentation made by Andres Lasagni, professor at TU Dresden, which will give us an overview of the project. Then from David Brunel from LASEA, who will explain how is the machine. Thomas Kredrowski from Bosch, who will explain about the process modeling and simulation. Dominic Bauer from Trumpf, explaining about 1.5 kilowatt developed for this project. Again, Andres Lasagni explaining about the scanning system and the polygonal D-lip system. And finally, but not less important, German Vergara from NIT explaining about the inline process monitoring system that has been developed. Finally, we will have time for some questions. By the way, after every presentation, we will have maybe 1-2 minutes for a quick question. So I leave the floor to Andres. There is a lot of interesting things to talk about. So Andres, please go ahead and tell us what is LAMpAS project.
Thanks everybody for coming to this meeting today, where we want to show you what we have been doing within the frame of the LAMpAS projects. It's a very ambitious project where we want to do many things for the first time. And probably you know what I'm going to tell you now regarding the motivation of our project, that it is very well known for many years that there are many plants, animals, insects that have special surface topographies with feature elements in the micrometer, sub-micrometer range. And because of these characteristics and very well-defined periodic or quasi-periodic structures, these surfaces, they have special functions. And this insect that we see on the screen is quite interesting, because as you can see, it has a very complex surface topography that is bringing at the first from one side the mechanical stability to the surface. These are the big features that we can see in the image, and the smaller ones are the topographical elements that provide an antibacterial property. That means also to create patterns with different length scales is important, and this is also something that we want to address in the LAMpAS project, or actually we are addressing. So, but it is clear, we have seen many research in the last 10-15 years where we see outstanding surface properties on small parts, and normally the processing time to create such part is quite long, so we have low throughput. Therefore, the only chance that we have really to bring these ideas, these concepts to the industry is to develop, for one side, a system that can provide high power, high laser powers. It's clear if we have more power, we can be faster in our treatments. But then with this power, we have to distribute it on the surface of the material to be treated efficiently at high throughput, and at the same time we need to create these very small features for making functional surfaces. Therefore, that brings us to the paradigm, let's say, regarding high power laser processing. We have from one side laser sources that work at very high repetition rate with relative low pulse energies. And on the other side, we have some laser sources that provide, of course, high power, but with a moderate repetition rates. And the question is how to create simultaneously high resolution features. And that's the problem with the actual situation, Therefore, we come to a scenario which is called number 3, where we put together two technologies that are well known. It's polygon scanner technology that has the capability to move the laser beam over the surface of a substrate very fast with speeds over 100 meters per second. And then what we do for getting high resolution structures is to use the concept of interference patterning, where actually now we are putting two beams together, creating a periodic variation of the laser energy. And in this way, if we have the correct angle, the correct configuration, we are able to get both things, high throughput and high resolution. Therefore, we make a couple of years ago, we started with the project LAMpAS, and we put all the partners you can see on the screen together for developing the different parts that are necessary to construct this unique laser machine. That means from one side, we have the development of the optics of the project. So where we are combining then the interference patterns with the polygon scanner technology. Then we have the development of a high power picosecond laser source, so delivering more than 1 kilowatt. We want to control the process. We want to know, we want to see if when we are treating these surfaces at high throughput, that we can assure quality. Therefore, we are implementing two different monitoring systems. Everything has to be put together into a machine. And at the same time, we want to know before which are the most important adequate conditions for treating different materials, in particular with different thickness, in order to avoid heat accumulation and at the same time having the maximal throughput. Therefore, in that case, we need to simulate, we need to know in advance how the laser interacts with the different materials. So shortly, the most relevant objectives of the project then are shown also now in this slide. From one side, we need to develop a high power picosecond laser source. From other side, then we need to develop a high spin beam delivery system with high resolution. So in order to create these multifunctional surfaces, we need to develop inline monitoring processes to assess the functional performances. We need to integrate all sub-elements, sub-modules into one system. And of course, we also want to reach different functionalities to get products with enhanced performance. And finally, okay, we need to validate the 3D prototypes in relevant environment. This brings us to the structure of the project. So here, just that you know how this project is running, we have 9 work packages. In the first one, we decided with the end users of the project, which are the most relevant applications where we can implement this technology. Also, how we're going to characterize the different properties using industrial standards. Then we started to develop the kilowatt laser source. That, of course, we will have different talks today on the different parts of the machine. Then we developed and constructed the first worldwide polygon interference patterning system. So we're really proud of that. Then, of course, we have 2 very interesting monitoring solutions for the process that are working very well. And Herman will tell about that later. Regarding the process simulation, we also have a tool where we can calculate temperature distributions on relative large areas, and simultaneously we can also calculate the topographies that are being produced in advance. And then everything is being installed into a LAMpAS prototype system by the CIA. So where all modules had to be evaluated in particular at high throughput. Then we had the demonstration and validation work package, so where we evaluate the functionality of the different parts. And okay, then we have some administrative work package, and of course, exploitation dissemination, what we are doing now here. This is done by EPIC. So thanks, EPIC, again, for allowing us to disseminate the project. So, and that was a short introduction of the project. So I'm very happy now that we can go through the different SAT modules, and I hope you will enjoy this workshop today. So thank you.
Thank you so much, Andres, for this introduction to this project. So just a comment, this project is what has been launched with very challenging objective, and it's very important and interesting to underline that, as we will see in the next presentation, has been achieved, these targets. And that's really is something making happy everybody about where we are. We are still to work the last month. This last month where we are the fine-tuning of the system, but the system is really working, operating. I'm wondering if somebody has some questions from, we have space for one short question. If somebody would like to ask something. Oh, I don't see nobody raise hands. So at this point, I will go to the next speaker. So this is really an impressive result. The machine, the first prototype that has been developed and assembled by LASIA. So it's a pleasure to introduce now David Brunel from LASIA, and we will listen, we will see, not we will listen, we will see what is this machine. David, the floor is yours. You are mute. Okay, good.
So, good morning, everyone. Thank you for the kind introduction. So, as Antonio said, I'm going to present what we call the LAMpAS machine. So, a prototype of machine capable of managing very high laser power, ultra-fast laser power. So, just to remind, so what the machine makes, actually it integrates several high-level components, meaning by we integrate a 1.5 kilowatt picosecond laser, which will be combined with fast delivery systems made of a DLIP combined with a polygonal head from ScanLab, and also some monitoring on the machine, like a camera and Fourier transform systems. So you can, as you can see, a first picture of the machine, which has been developed and designed in order to be quite easily installable in almost all kinds of facilities, industrial facilities. Just to give you an overview. And so such machines, so as I said, can be installed in almost any industrial facility or laboratories. So here are more details about the machine itself. So as I said, it's a quite compact design, as it has been designed around the laser, which is the most important part of the machine, of the full prototype. And at the end, with a reduced footprint, also with some easiness in the maintenance has been also foreseen, like for example, by putting the laser on a drawer with wheels. So the laser can be easily removed and put back in case of maintenance if necessary. In terms of dimensions, so the laser dimensions are of 2.2 meters by 1.3 meter. And the footprint of the machine is of only 2.6 meter by 1.7 meter only, with some advanced features like a beam stabilization system, which has been foreseen as well. So why we have done that is because by using high average power, we have learned through the project that the air can be heat, can be warm, and so could generate some what we call beam jitters, so kind of tiny oscillations of few tens of hertz due to the air itself. And so the beam stabilization system, which has been foreseen in order to correct this in real time, and which is composed of two positioning mirrors, motorized mirror, and two positioning sensors. It is also capable, and this is an important point, because it is also capable of a wide intensity dynamic range, meaning that it can work for powers with a factor of 1,000, meaning, for example, from 1 watt up to 1,000 watts at the same time without adjustment. So the machine also integrates the high-speed delivery system, which is made of the combination of the DLIP with a polygonal head. So at the total, which is quite heavy, we are talking about more than 40 kilograms just for the delivery system. It has been integrated on a Z stage in order to have a very high accuracy in terms of positioning. So the focus positioning is very accurate, below than 5 microns. And also, so this delivery system is capable of very fast scanning with speeds that can go up and even more than 200 meters per second. And this over a line which is of 300 millimeters wide. The machine also integrates some monitoring systems, inline and offline. So, for example, the infrared camera developed by NIT, which will be presented later, which looks at the process in real time, and as well FFT measurement system. So once the patterning, once the texturing is made, this fast Fourier transform system can make some analysis and get some information from the results of the machining itself. Also, the machine has been designed to be capable of processing large surfaces with high power. So we are taking advantage of this high power, and for this, the beam path has been designed in order to being able to manage such high power. So, for example, one first important thing is to use high reflectivity mirrors, which are designed to be more than 99.9% of reflectivity, but in reality, we are more close to 99.99% of reflectivity, as you can see on the measurement of the reflectivity. We also have a control of the divergence, which is very important in order to control the focus position and also the crossing of the two sub-beams on the workpiece. Also, as well, at the same time, to keep quite a good control of the beam size itself. This in order to have control of the spot size, meaning, for example, in this case, we are looking at getting quite large spot size on the workpiece in order to have a fast processing. Also, another thing which has been developed is what we call a compensation system. So this system is to keep a constant optical path length. This in order to guarantee that the processing results will remain the same wherever we machine on the area. So we have here a machining area of about 1.5 by 1.5 meters. So, and thanks to the systems, we can guarantee that the process will be the same on the full area. So we also have designed the optical path in order to be dust proof. So all the optical components are protected from the dust. That we use some optical boxes which has been which have been assembled under a clean environment and then closed. And this, so wherever we have to work on optical, it can be the laser or it can be optical boxes, can be done on site in a proper environment. So that we reproduce actually a class 5 white room environment. So here are some first results that we got so far with only 160 watts so far. But we can also already see that we were able to machine first samples of 250 millimeters by 300 millimeters. And this were done with only 3 minutes, thanks to the machine. In terms of characteristics of this first result, we had a period of about 7.2 microns and a depth of about 0.1, and that will be optimized in the future. So here are some other demonstrator which has been shown at the Munich Fair during in May, actually. So here we can see a very nice diffraction effect thanks to the pattern that has been made on the surface of the sample. So just to remind that we have the pattern is made of different scales at the same time, as Andres mentioned before. So we have the interference patterning, and at the same time we also have some LAMPAS patterning applied on the top of this. So we have at least 2 scales at the same time on the surface. So regarding the next steps, so the laser will be upgraded to 1.5 kilowatt, which is currently ongoing actually. And then there will be a validation of the monitoring systems that have already been tested in the LAMPAS system before on the texture part. And also obviously, so an increase of the process speed and optimization of the process itself by raising the power up to 1.5 kilowatt, obviously step by step. But indeed, we aim to reach 1 square meter per minute. So this is another overview of the full consortium, and thank you for your attention.
Great. Thank you so much, David, for the explanation of the machine. Clearly, the machine now looks so easy, but it really takes a lot of efforts to every single part must be really fitting with the other part of the system. So it was really a complex system. Maybe just a question. I see no question from the attendees, but maybe I make a comment question. Which was the most challenging? Just say which was the biggest challenge that you had making this machine and testing the machine?
Well, there were several challenges. The first one was mainly the reduced footprint. We did not want to have a machine or prototype in different pieces. We wanted to be as close as possible to industrial applications. And so the full design has to be thought from the beginning of the project. And also at the same time to take into account all the constraints from the different components in order to be as close as possible to industrial prototype. I'm saying prototype because it's not yet a commercial machines, but indeed, that was maybe the main challenge in order to have a reduced footprint. And also the maintenance. So as I said, we had to think from the beginning that as this is a quite challenging project with a high power laser, so we have to take into account that there could be some maintenance on optics or laser or components, whatever they are. And so this maintenance also has to be taken into account from the beginning of the project itself.
Good, very good. And I think that here speaking about maintenance and also, yeah, this is it has been designed as a production system. So it is in theory 24/7 machine. So I see a question from Constantinas from Optoman, probably something related about maintenance of the optics.
No, no, not this time. My question is a bit more simple. Maybe I missed it. Maybe you mentioned in your presentation. What is the current throughput of the system and what you expect after upgrading the laser, the throughput of patterning?
So in terms of, so this is related to the processing speed. So far, well, we have done only first tests. As I said, we could reach a surface, we could texture a surface of 250 millimeters by 300 millimeters. Actually, the 300 millimeters, this is the length of the line of the polygonal head. So we can do that at once. And the surface has been made in about 3 minutes. Yeah, so far. And that was done with only 160 watts so far. But as the laser is upgrading to 1.5 kilowatt, we expect to reach a lot faster speed. We still have some optimization that can be done on the process and optics to increase the speed. The aim of the project is to reach 1 square meter per minute.
Okay.
Okay, thank you. Yeah.
Thank you, David. So here is becoming, okay, after the first question, I see that there are other 3 questions coming. I will invite Tamara Delgado from Hyman to switch on the camera and make directly the question, please. And then we will have AGC, Free Li Quang, and Paul Blair from Power Photonics. Please, Tamara.
Sorry, because I have some noise here in the room. Okay, I just was thinking about the maximum laser power used till this moment for the experiments, for the tests.
So far we have used maximum power of 160 watts, and we are working on maybe doing some tests at 200 watts. But at the end of the project, we should have on the workpiece, we will have 1.5 kilowatt coming out from the laser head. And on the workpiece, we expect to be about 1 kilowatt, something like that.
Yes, it's important also to explain that the project used 2 laser sources. One was the preliminary laser sources to speed up the assembly and the testing of the different components. And now in the last phase now, they are installing, let's say, the big brother, the big laser of 1.5 kilowatt, but also it's necessary to ramp up the power slowly because it's necessary to check the situation. But let's say, we have still 1 month. There is a lot of time, let's say. So I see then that there is a question from AGC. Quang, please, go ahead with your question.
Hi, thanks for the presentation. And I have some questions. So what is the focusing tolerance of the machine? For example, when you're processing on polymer or thin foils, I assume that the material will not be perfectly flat. So when you have some waviness on the surface,
So
is the tolerance you have?
Okay. So here, actually, thanks to the DLIP technologies, we are using well, thanks. We are using, so we are combining the DLIP and the polygonal head, which at the end we have a quite long focal length, which is from memory from 180 millimeters, between 180 and 200 millimeters. So that gives us a very long depth of focus. And in terms of interference, in terms of patterning, we have a few, from memory, between 1 and 2 millimeters of tolerance on the focus, where we can get those patterning thanks to the DLIP.
Okay, yeah, thanks. That's interesting, impressive. And another question is the machine basically can process the surface like 1 meter by 1 meter, even more, but the polygon scanner is only processing 300 millimeters, as I remember. So it means you have to move the polygon scanner on the surface. And at the boundary between the scan area, how uniform is it?
So we haven't worked on the boundaries yet. This is actually the project is ending in 1 month, but in any case, we are willing to carry on more tests and developing more adjustments and optimization in the future, like this one, for example. And we know that the polygonal head we have can be very accurate. Also, a combination of the polygonal head and the laser, the synchronization with the laser can provide very high accuracy in terms of boundaries on the edges of the processing frame window.
Maybe
Okay.
shortly from a comment from my side for the many of the target applications we are looking, the tolerances are quite not so important because the functionalities that we want to reach are quite flexible to get. Of course, in the aesthetical case, then it's very important, but for many other applications, it's not so critical. So it's not an issue for many functionalities.
Okay. And sorry, I have a third question. So I imagine that right now you're using 160 watts laser. So when you upgrade to 1.5 kilowatts, I guess the requirement or the environment that you use the machine in, then also the maintenance, it has to be improved, I guess, because with higher power, if you have any contamination and stuff, it might be quite dangerous for the optics.
Yes, the optics have been thought to be normally well, we already know that, for example, all our mirrors are okay for 1 kilowatt femtosecond lasers. We have tested them, so we have no worries about the mirrors. We are at the same time, and in the frame of the project, we have also investigated some other optics, at least inside. I will not answer regarding the polygonal head but for the machine side, we are confident on other optics. We are also investigating like new kind of lenses that should be capable of to be okay with very high average power, with threshold damage much higher than the standard lenses.
Okay, thank you very much for the answers.
Okay, then we have just space for a very short question, the last one before to go to the next. Paul Blair from Power Photonics, please. Yes, okay. It's a short question, maybe a long answer, but we'll see. I was curious what demands the system made on the environment in which it exists in the clean room, things like temperature stability, you know, for the laser control and also just to control expansion and things like that. Does it make very high demands on the clean room, for example?
I'm not sure to have understood the question, but in terms of environment,
do you need to control the temperature of the clean room very, very accurately to ensure that the system is stable?
Well, so far we haven't investigated this so far, because our lab is we have a control of the temperature in our lab. We are between 17 and 18 degrees in the lab, and we also have a constant humidity rate. But in any case, as I said, all the optical boxes, all the optical path has been designed and assembled under clean environment that we have here. Not in the room, not in the lab, but we have a movable roof that provides clean air environment where we can assemble, and we can move this part over the laser, for example, if there is a need of maintenance. Okay. Okay. It'd be interesting to see when you run this, and you're perhaps running it over. I don't know if there's ever a case where you need to run it over many hours or 24 hours or something like that, whether the fluctuations in the temperature will mean that things are expanding, contracting, and that may alter the pattern you're making and things like that, and whether control will be needed to be added at that point. Yeah, that's something we will have to investigate. As you said, this is a production system. The aim is to be a production system, so that's the things we are taking into account on our standard machine. This is what we take into account, and we have to do the same kind of thing with this machine, obviously. Okay, thank you.
Thank you both, David, for the great presentation. And it's time now to go to the next presentation from Thomas Kieredrowski, Bosch, about the modeling and the simulation, because also simulating in advance the process and the results is very important. Please, Thomas, the floor is yours.
Thank you. And I try to share my screen.
Is
No.
not coming yet. Now is okay.
Okay, perfect. So my name is Thomas Gidowski from Robert Bosch, and our part was to modulate and simulate the process itself. And the main goal was to understand a little bit more over the process and especially the limits of the process. So the simulation should use to accelerate the development process for the DLIP process, to find the suitable processing parameters. And for us, it's very important that this calculation can conducted on a common notebook, so that the simulation is not so complex and it's easy to calculate for a notebook. And therefore, we used for the simulation analytic equation for the heat distribution. So we had on other projects in the past good experience with this method, and so we adapted this to the DLIP process. The first step was to modulate the special fluence distribution for the DLIP optics. So we have sorry, we have the normal beam distribution of a Gaussian beam, and on the other side the interference pattern, and both together gives us the interference pattern on a Gaussian beam. So this is the distribution of a normal DLIP optics. And just for demonstration here, I calculate a very small spot from 20 microns diameter, because the spot size we aimed in this project of about 150 microns, we didn't see the structure in this beam here. And we calculate or simulate two different things. On the one hand, we calculate the ablation depth of the process. So we use for that a very common equation, the logarithm equation, that can calculate the depth of the ultra-short pulse ablation. And in this case, with our interesting intensity or fluence distribution, the DLIP structure. And on the other hand, we can calculate the temperature. And for this, we use this equation for the heat distribution in the samples. In the first step, we conduct the calculation for very common parameters with classical old, I would say, old DLIP optic, with a low rep rate, with very low power, with low pulse energy, is to try to validate the simulation. And here are some older pictures from the DLIP structuring process. You can see different patterns. These experiments are done from the TU Dresden. And on the other hand, the depth of the ablation with the structure. And you can see here, for this point, I calculate for 20 pulses and the pulse energy and fluence and so on. We get here 1 micron depth from the experiments for 20 pulses, and the same 1 micron I get in the calculation for the overlap with 20 pulses. So that was very good for the first try. But then we concentrate on the main challenge of the process development for the high-speed DLIP structuring, and this is the heat accumulation. And to get a deeper understanding of this heat accumulation or the effects on the process, we used a process with a preheating experiment. Here on the side, again, these experiments are done at Dresden with a standard DLIP optics. And here we have a heat plate, and this heat plate can rise the temperature of the sample here to 250 degrees Celsius. And then with this higher temperature, we made the structuring experiments. And the results of these structuring experiments was surprising, I would say. It was interesting to see that the effect from our opinion, was very low temperature of 250 degrees. So it's not so much in terms of heat accumulation at a laser process, but even at that very low temperature, you can see a big effect on the structuring result. Here you can see in a diagram above the DLIP structuring like it should be at the normal room temperature, and at 250 degrees, you can see the structure is very low, or even it's hard to see the periodic structure of the DLIP process. So that means that we have to find parameter and process strategies that keeps the sample pretty cool. And therefore we calculate larger areas. And for this example here, I showed on the slide, we calculate different thicknesses of the metal sheet. And you can see here the influence of the thickness, for example, 800, 400, and 200 micron thickness. And that these thickness had a big effect on the heat accumulation on the sheet. Here the blue area is room temperature, and the red area is more than 100 degrees Celsius. So the scale is here on Kelvin, degree of Kelvin. But you have to know that this 200 micron thickness of the sheet means that there's no support under the sheet. So in the case we have support under the sheet, for example, copper for cooling or so, the heat would be very different from this. This is a sheet on the on the calculation. So the result from the calculation experiment was that the simulation of heat up the calculation of the ablation depth and the calculation of the heat accumulation was very fast with the equations, and we have some interesting result in terms of what that the process is very heat sensitive, and some advices for the process. So we need high repetition rate with high fluence to get a high throughput, but in order to keep the temperature of the sample low, we need also very high speed to reduce the overlap at high repetition rate, and we need spot size as large as possible to get higher throughput. And the thickness of the material is important. On the one hand, you can take thick material to cool the material itself, or thinner material with a heat sink under the material. So thank you. That was a short introduction to the simulation works we done in this project.
Thank you so much, Thomas, for the very extensive presentation. Clearly here we are touching a very important point, is the modeling of the processes. So in this moment, the laser is no longer a bottleneck. The laser can achieve nearly every kind of power level, but now we are going to understand and to see which are the process problems or the process aspect. And the modeling is really a relevant part of this task. Anybody from would like to comment or make question? I see nobody is raising the hands. Maybe if nobody is still thinking about this topic, I will go on with the next presentation because we are a little late. So now we are going into the laser. We were talking about the laser. So Dominic Bauer from Trumpf will tell us about 1.5 kilowatt ultra-fast laser. So that is the key point. Dominic, please, the floor is yours.
Thank you. Can you see my presentation?
Perfect.
So I'll present today the results mainly produced by Johanna for the 1.5 kilowatt laser development and also the inherent goals we wanted to achieve within the project. So for the system, we have a high power ultra-fast laser source. This is usable for processing of transparent materials. Also, we can use it as a driver for a secondary source, or you can produce a filament as shown here on the Centis with such high power lasers. But in the LAMpAS project, we want to use this, want to produce these DLIP structures and process fastly large surfaces, as David already showed. And therefore, we agreed during the project on several laser parameters. I put here the key parameters of the laser. It should have 1.5 kilowatts of output power, a flexible repetition rate of 250 kilohertz to above 2 megahertz. So a reasonable pulse energy, and also the high repetition rate for the polygonal head structuring. So the pulse energy is limited to 4 millijoule in this case. Pulse duration is 3 to 10 picoseconds. This is mainly due to the fact that we want to have an interference on the material, and therefore the bandwidth of the system needs to be narrow. We agreed on a beam quality below 1.6. In the end, it turned out to be better. To achieve this, we picked one laser of our huge variety of micro lasers we have. Among these are fiber lasers, disc-based lasers. We used a SLAP ultrashort pulsed amplifier, and we post-amplified this. I will show this in a few slides. Oh, sorry, this has been skipped. These lasers can for sure be used among all possible things you want to do with the laser. So micro drilling, PCB cutting, glass cutting, also glass welding, and they can be used as a secondary source. So we took one platform here, the TrueMicro 6000, and combined it with our to-this state-of-the-art technology. Here, up to 20 kilowatts from a single disk can be produced. To make this, to realize a ultrashort pulsed laser with that technology, we went and built a multi-pass amplifier within the project. So here we are able to amplify almost all kind of pulses, pulse length, pulse energies from this 200 watt level of the TrueMicro 6000 to 1.5 kilowatts. Therefore, we use a thin disk on the one side. We fold the beam multiple times over the thin disk. I'm sorry, I'm fighting with the trackpad. We fold the beam multiple times over the thin disk by using a mirror array, which is shown on the right side. There, several individual mirrors are placed on a glass plate. They're welded on the glass plate, so this is an all glass construction which is not moving or de-adjusting, misaligning. And these two parts, our robust thin disk and the glass plate, are then mounted in a tube shape, and they build a multipass amplifier module which can be used to amplify these 200-watt level lasers up to 1.5 kilowatts. And that, on the next slide, I want to put a little focus on the mirror array. So this mirror array is built using a robot-assisted glass welding machine. So each individual mirror is placed on the glass plate using a robot, assuring constant quality. And then it is welded using our TrueMicro 2000 in the femtosecond regime and the top weld optics. And this is shown on the right side. So from the lowest, the mirrors are placed from the upper side, and from the lower side, then there is a plasma generated inside the glass, which is then joining the two glass components and creating a rigid joint of them. And you can see here this was a test weld where you can see there is a bright plasma shining, and in the end these two glass parts are joined together and they are not moving and afterwards. And this is used for our high power ultrashort pulsed lasers to have maximum stability within this laser. So let me jump to the LAMpAS laser we are currently setting up at LASEA. So the laser consists of an adapted TrueMicro 6000 with a smaller spectral width. Then there's so this is depicted here in this picture here. Then there is the multipass amplifier next to the system, and we built for this demonstrator we built a beam guidance which incorporates the modulator, the post compressor, and the safety shutter. And all these components are then housed within a housing to be able to operate it in the machine where there is no constant clean airflow. So the seed parameters, the seed laser we used had up to 285 watts. The repetition rate was, as shown, from 375 kilohertz to 2 megahertz. The pulse duration we received here were 8.5 picoseconds. This is already pre-compressed, and the pulse energy was already 0.76 millijoules at maximum. For sure, if you change the repetition rate, the pulse energy goes down. And that has been amplified with the system to up over 2 kilowatt. Here on the left side, you see the output power, and on the right side, you see the M squared. We have a reasonable good M square up to the operation point where the LAMpAS machine is working. We achieved 1.6 kilowatts with 4.3 millijoule with an M square of 1.32, which is will be used for this processing in the LAMpAS machine. The system is now shipped to LASEA and is currently installed by Johanna, and we are happy to see the performance inside the machine, and also the performance of the machine to produce large surface structures within the project. Yeah, just to summarize, we need high power and high pass energy for high productive systems. In this case here, we use especially the high power. A variety of material processings can be done. The systems need to be industrially stable and reliable. And we thank for sure the EU for funding this project. And with that, I want to conclude and thank all the project partners, and thank you for your attention. And I'm open for questions.
Thank you so much, Dominique, for the great presentation. A really impressive number. I was smiling a little when you said limited to 4 millijoule, because this is, in this moment, is really not a limit, but it's really a great number. 4 millijoule in the picosecond regime means gigawatt peak power. So that is a really impressive result of the project. And there is anybody that has some curiosity, some question? Here we have one of the specialists of truth that could answer about this laser. I just look around. I don't see any comments yet. Okay, so I will say we are a little late, so I go on with the next presentation. In this case, about the polygon and DLIP system developed by TU Dresden, and we have Andres Lasagni who will explain also this other important piece of the puzzle. It was really a crazy puzzle to assemble this machine. Please, Andres.
Yes, so we'll start. I hope you see now the correct screen.
Yes.
Okay, so yes, so now I'm going to introduce some details on the first worldwide DLIP polygon module that has been constructed together, of course, with ScanLab. Actually, the action was led by ScanLab. And before I go to some of the details, I would like to show you this slide where actually explains a little the philosophy, let's say, behind the project. And remember, we want to reach high throughput of several square meters per minute. At the same time, we need resolution, in particular for the target applications. We identify that we need a spatial period about 10 micrometer or a little shorter. And this is the situation that we have today in some cases. I mean, we are already working with interference patterning for a long time when we're using nanosecond pulses. In some cases, we're already at high throughputs, like 1 square meter per minute. And polygon scanners, as you know, are very interesting tools to reach high productivity, but we need to reduce the feature size. And that was the reason why we put all these technologies together. So to get high throughput and high resolution at the same time. And because of the typical properties, I mean, typical interaction of laser radiation with materials. So we have here high flexibility that we can treat different materials, which means we can address several functionalities of different materials. So therefore, the challenge for us was how to reach high resolution, high throughput, and large area all at the same time. And that's why we come to this solution. So the polygon scanner interference optic is a key element, of course, together with the laser source for achieving these productivities. And after analyzing the different applications we wanted to address, we come to these parameters that you can see in the slide. that our target was to reach a spatial period of 10 micrometers or shorter, which means that we have a feature size that is about half of the period. We can say is 5 micrometers. Based on the simulations that you have seen before, we also identify we need large spots in order to avoid heat accumulation, and clearly we need to treat large areas. Therefore, we define a scan field of 300 millimeters also. Also, for controlling heat accumulation, increasing throughput, we need moderate or high pulse energy, and maybe the comment from Antonio for some minutes ago, these 4 millijoules that are important in our process. And then, of course, to be faster, I mean, to reach high throughput, we need scanning speeds over 100 meters per second in order to avoid heat accumulation and so on. So then, after that, we started with an analysis of the requirements for both suit modules. So we have a LAMpAS polygon scanner that is combining 2 suit modules. From one side, we have the LAMpAS module. Of course, it has to withstand high energy and high power. So remember, more than 1 kilowatt, and pulse energy is up to 4 or 5 millijoules. Then it has to split and deliver 2 beams to the polygon part of the system. And this is really a critical issue because we have to assure that both beams are traveling exactly the same distance. That means they have exactly the same optical path length. Imagine that a 10 picosecond pulse is 3 millimeters long. So if you have few differences in the optical path length, then the beams will not temporally overlap perfectly. And this reduces the contrast that we need for the laser treatment. Of course, laser safety is an issue, like always. So we also have to have a very adequate unit in order to protect the user for these very high power levels. And in case of the polygon SAT module, so we need a larger spot, of course, also has to work with high average power, high pulse energy. We need an interference angle, because this is important to control the period that has to be larger than 6 degrees. And this is not easy at all to do. You will see that we come with a very new design. And okay, then we have to maintain the interference pattern along the scan length to assure well overlap when control of the beam size and so on. So before we started to go to the final solution of our LAMpAS machine, of course, we did some preliminary results to understand about the process. So we combine a polygon scanner with a beam splitting unit, and we use a picosecond source with some hundred of watt of laser power. And we were looking, okay, the limits, what can we reach with infrared? This is also important. We want to process with infrared because we don't want to lose energy. So, you know, when you go from infrared to green, normally you are losing 50% of the power. So then we make this test to demonstrate the possibility of working with the technology. We use a polymer material in this case. Why? Because it has a very low threshold. And this allows us to see very well how is interaction of the laser beam with the material. And you can see here some lines that have been created at 100 meters per second. So in this case, even we are not having ablation, we're having something that's called swelling. So the polymer, the pigments of the polymer absorb the laser radiation. They create some bubbles because it tries to decompose. The bubbles get trapped into the material, and therefore you have this swelling. And what we observed in about 70 micrometers was the spot size. We have like 2-3 interference lines. So, and you can see that's quite well possible to control I mean, the quality of these lines. So the scanned lines are separated in this case, but of course, as you can see now in the next image, you can control the hatch distance, let's say, between these lines in order that you get much better homogeneous structure. So in this case, so with 21 micrometer period, so we were able to reach a throughput of 1 square meter per minute for this polymer. Remember, has a low ablation threshold, but clearly the period is too large, and because for the functionalities we want to reach, it is clear we need smaller feature sizes. Therefore, we have to come to a totally new design, and lamentably I have to show you something close. I cannot show you all details, all the technology that has been implemented in the design of the LAMP polygon system. But we come with a solution that is quite compact, where we are having on the top part, on the upper part of the system, the part that is dedicated to the beam splitting unit, keeping some specific properties, let's say, of the laser beam, so that we can overlap them with high precision. And after that, okay, this was the first time that the unit was constructed. So you can see here how it looks like. And now this is how it is now, I mean, at LASIA in the final LAMPAS machine. I would like to show you some preliminary tests that we did almost one year ago, so that you can see the different spots. So here we enhance the scanner speed and work with a lower or relative low repetition rate, so that we have, for example, here you can see on the top isolated spots. You can see the spots are about 170 by 150 micrometers. It was exactly the target for the polygon LAP module. You see also the interference lines, which are very well defined into each individual spot. This means that we have a very accurate path length. Again, both beams are traveling more or less exactly the same distance. This is important to get high contrast. And then, of course, if you overlap the spots, you can get deeper structures. But here, what is important that you see is that the lines are very well aligned along the whole area. So this is a video of the first setup for a long time, showing the capability of doing these patterns. So just now to summarize, we can say that from the LAP polygon module, we have demonstrated for the first time that it's possible to construct, to create, and to process materials in this way. We even reach resulting spatial period that was 30% smaller than the target in LAMPAS, that will allow us to enhance the surface properties, and important to mention with infrared radiation, because the period of interference pattern is strongly depending on the wavelength. And then we also reach the scan field size of 300 millimeters. And of course, by controlling then the scanner speed and the repetition rate of the laser, we have an independent adjustable overlap for the system. And this allows us together with ScanLab to make a joint patent. That is one of important results of the project, and that we want to, of course, commercialize in the future. So with that, I again would like to thank all project partners and thank you for your attention.
Thank you so much, Andres. This is another impressive presentation about the results about these subsystems. So every subsystem here is so relevant and so important. I don't see nobody from the attendees raising question. We are a little late, so I will proceed directly with German Vergara from NIT. So we discuss about the inline process monitoring, what is really closing the cycle around this machine. Please, German.
Yes, so just let me to share my screen.
Yes, sir.
Can you see?
Yes, sir. You have to go in presentation mode. Great.
Okay.
Let's go.
Let's go. Good morning to every people. I would like to present the progress done in line process monitoring system. Just to say that LAMpAS is a laser-based process as industrial laser process will try to be, and it's very, very important to install or to integrate inline monitoring systems because they are. Let me to start with explaining more or less the objectives of this working package. Also, I would like to show you what is the concept developed, some details about the heat accumulation sensor and topography sensor, some preliminary results, also the integration of in the LAMpAS prototype and so on. Okay, the objectives. We have tried to develop a system able to monitor inline key process parameters and characterize in real-time pattern structure producing during the treatment. We started, the first step was to define the requirements of the monitoring system. Also, we make some tests, preliminary tests with the existing sensor. We develop more modern sensor adapted specifically to the application, set up and commissioning the monitoring system, and we have done some tests, preliminary tests, and analysis of the results. This has the requirement definition. The basic requirement definition of a sensor was, of course, it has to be useful for real-time information of process. I mean, the information provided by the sensor has to be useful. It's very important. It has to try to assure the quality during the process. Very important thing is has to be very easy to use. Of course, they have to be compatible with the LAMpAS prototype. These are the basic requirement of the sensor developed in LAMpAS. The type of parameters that we would like to test was fluence fluctuation, the effects on treated surface, beam quality, instability, and robotic parameters, and other type of instability. This is the main goals of our sensor. We decided to use two independent techniques. One of them was to use a high-speed infrared imaging for measure in real time the heat accumulated, which is a very important parameter for this type of application, as Thomas explained before. And the other technique was a fast Fourier transform based system, which gives us information about the topography of the textured surface in real time. Oh, sorry, I have to go. Okay, this is the concept. The concept basically was to try to install inline the sensors in real time, and the infrared camera we was watching the texturing during the incident of the laser, and the fast Fourier transform sensor will be testing the topography of the textured surface. Just I would like to describe a little bit about the infrared sensor used for heat accumulation. It was based in a previous camera that NIT has. but we make some improvement on adaptation. The first adaptation was in the acquisition. We modify the chip and for obtaining snapshot images. This is a very important thing because the LAMPAS process is very dynamic process, and we need to get all the information of pixels at the same time. We also increase the velocity from 2 kilohertz to 4 kilohertz or more. Again, it is very important for the dynamic process. And also we also implement some improvement like a non-uniformity correction by hardware and also a flexible window. This is are the adaptation that we make in our infrared camera. You can see here some preliminary result of demonstrate the feasibility of the technique, and you can see here how it's possible to see the heat accumulation depending on different parameters of the process. In this case, the parameter was the frequency, and you can see how the camera was able to test the heat accumulation during this type of process. We have done also some tests with a polygon scanner plus LIP. This is very close to the real LAMPAS process, and you can see here how is dependent the dependency of the infrared signal, which is the heat accumulated, with the overlap. You can see here the 50 meters per second has a high temperature, high heat accumulation, and when you increase the velocity to 200 meters per second, the heat accumulated is much smaller. Also, we use the second technique was a fast Fourier transform analysis. It was completely developed by Dresden University. Basically, it's a well-known technique. We use a laser pointer, and we with a CMOS camera we obtain the diffraction pattern of after incident with the surface. It is a very convenient technique for this application. In order to show the feasibility of this sensor, we can demonstrate that with this example. You can see here four different type of areas. The number one is untreated area. The number two is a area treated with a hatch of 0%. The number three is an area with a hatch of 25%, and the number four is an area treated with a hatch of 50%. I can show you an example of how it works. You can see here in this graphs below what is the area, the first and second order. It's very impressive to see how this technique is able to select or to distinguish between the different type of texturing. Only obtaining information about the area of a second and first is really impressive. This is the type of technique that we will use also for monitoring this system. Okay. But we have also done some tests for combining both the information from the infrared, highest infrared camera for heat accumulation and the depression order area. It is possible to see how, I don't know how to say, how easy it is to distinguish the good and bad surface quality. bad surface quality will be the red dots, and good quality will be the green dots. It is you can see here in the x-axis is the infrared signal, and the y-axis is the area of first or second order. It is remarkable to see that it is very easy to distinguish when the temperature is going high, which means high infrared signal, the first and second order area going down. I mean, this is a demonstration that the combination of both techniques can be a good solution for assuring or for assessing the quality of the texturing process in real time. This is the objective of the working package. Okay. Okay. Okay, this is I think David showed before, but this is basically the monitoring system installed in the LAMpAS prototype. And you can see here the infrared, high-speed infrared camera for heat accumulation and the fast Fourier transform sensor head for topography assessment. This is the working area, and it is ready for showing the quality. In summary, new concept for inline monitoring system for Russian testing process that has been developed. We have developed two different techniques or two different types of sensor: inline heat accumulation assessment with a high-speed infrared imaging camera. Sensor 2 is inline topography assessment of structural surface based on fast Fourier transform based sensor. Both sensors has been developed and tested and adapted to the application. Preliminary results are really good and demonstrate the successful proof of concept. This monitoring system is integrated in LAMpAS prototype. That's all from my side.
Thank you so much, German, for the presentation. Please, if you can stop sharing, it's really impressive also in this presentation. We are really on time. Just a recap what we did today. Today, we presented the final results of the project LAMpAS with the key objects coming out from this project. So the LAMpAS machine, so the prototype of a machine able to process large surfaces, and also other relevant part of this development. So the study and the work done for modeling the process, the 1.5 kilowatt laser, ultra-fast laser, the optical system, the first in the world DLIP system with polygon. And last but not least, also the inline process monitoring system that has been integrated in this machine. I can't comment as saying that for EPIC was really an honor to be and a pleasure to disseminate such awesome results. And I will leave the final words to Andres, the coordinator of this great project.
Okay, thanks, Antonio. And I would like to thank everybody for being today in this presentation. There will be many things coming out until the end of the year, I think, even after the official end of the project regarding the LAMpAS. I think we have really the chance, or we had the chance to make something unique with a lot of challenges, putting things for the first time together. And I also quite sure that this project will open the door for many other applications and ideas and concepts for the future. So again, everybody, thanks a lot for being here, and I wish you a nice rest of the day and also a nice weekend. Bye-bye.